Welcome to the class of material selection for mechanical design. Now, we are in the week 3 in the realm of crystal structures. Okay? And there is a very important way. In the last class I told you that how crystal structure, the crystal formations, different types of crystals, how that can affect the mechanical properties of a system. Now, there is an important way to quantify this effect, and that can be done with the help of something which is called Miller index. So, I am going to talk today on the significance of the crystallographic direction and plane and how you can quantify them with the help of Miller index, and using Miller index how you can measure the linear and the planar density. And finally, so this is something which you will also see in nature and properties of materials, okay? But we are not stopping there. Finally, I want to show you that how these inference that you will get on the linear and planar density is going to help you in material selection, and corresponding to two cases we will discuss. That is, one case we will discuss corresponding to a turbine blade of a very high temperature. So, this will be one case study we are going to do at the end once you understand, and the other case study is just a quick comparison of these with respect to what you call a car body. Okay. There are different models of car body. We will consider a specific model which is called body in white, or in other words the BIW model. Okay. So, this is what is our goal in this particular class. So, let us try to go point by point. First of all, what is the significance of crystallographic direction and planes? Now, the crystallographic direction actually can give you an idea about the deformation under various loading condition, because it is the crystallographic direction that controls a very important parameter called slip. So, slip and dislocations, I will talk about it in another lecture in a much more detailed manner, but it is sufficient to know now that these slips or that initiates the deformation occur on certain crystalline planes and in certain crystallographic direction. So, these two, the plane and the direction, that we should be able to quantify it. Once we know that, we will be also able to know that what will be the mode of material failure, so that depending on the application we can safeguard ourselves against such failure. Now, it is not only true for the mechanical properties, but also this concept will be important towards electrical conductivity, thermal conductivity, and elastic modulus. I already told you, which comes under the mechanical property, magnetic property and piezoelectric property also. These are all orientation dependent. So, the concept is very powerful. It will allow you, in other words, to not only understand the anisotropy in terms of the elastic effect, but also in terms of various other properties such as the electrical and magnetic and the thermal properties or piezoelectric properties of a system. Now, immediately you have to think of it, okay, what is the application of this concept, right? So, you look at it, for example, the turbine blade. Now, efficient, strong, nickel based single crystal turbine blade is something which is always desirable. All the high speed turbine blades of the aircrafts, for example, 30,000 revolution per minute, these are all made of nickel based single crystals, okay, that can withstand high temperature because there will be no grain boundary, because it is a single crystal. If there are polycrystals, there will be grain boundaries. So, that is one, and also they have different directions of close packing, and that will influence the decision, such as for FCC structure of nickel, it has a close packing direction of 110. So, that is the Miller index contribution to the choice of the material. I will come to it towards the end. Another application is for the gallium arsenides, which are used in CD players, for example. Now, they are again grown from single crystals along 100, and that is also important because this system is subjected to a high centrifugal force. So, you have to arrange the crystal direction accordingly to sustain the centrifugal force. And then you think of the computer chips. They come from silicon wafers, and they are generally sliced from single crystal silicon grown along 100 direction. So, in each of these cases, you see it is not only sufficient to understand what material you are going to select, but also the crystal orientation, whether it will be a single crystal or polycrystal, and if it is a single crystal, then what will be the direction, the preferred direction of the crystal. Those are the things that becomes important, and that is why the Miller index becomes important for us. So, Miller indices are essentially the designation or quantification of the planes and direction in a unit cell. Okay. So, everything in Miller index is defined with respect to a unit cell, right. So, something which is like unit in each and every direction. Okay. So, 1, 1 and 1, right, and let us say you have the origin here. So, you can keep the directions x, y and z. So, that is the unit cell. Okay. Now, the number of indices which will match with the dimension of the lattice or the crystal in a 3D unit cell, we will define this index in terms of HKL, but keep in mind that there is no comma after H or K or L. Okay. So, if there is no comma, then only it becomes an index, otherwise it will become a 3D coordinate, a point. Okay. Another important things we have to keep in our mind is that if it is a half moon bracket, that would always mean that we are indicating an individual plane, right, like 1 0 0. Okay. So, that means x is 1, okay, along this, and then y is 0, z is 0. So, that means this is an individual plane, this plane. Okay. So, that is what is the half moon bracket significance. But if it is a curly bracket, then that would mean a family of planes, that is 1 0 0 curly means it can be 1 0 0, 0 1 0, 0 0 1. That means it can be this plane, it can be this plane as well as this plane. So, all the 3 planes. Okay. That is what is the curly bracket stands for, a family of planes. If I use a square bracket, then that would mean an individual direction. Okay. So, that means, for example, again I am just redrawing it for you, that suppose I have a unit cell like this, and then suppose from the origin I want to indicate a particular direction. Okay. Then this would be with respect to the square bracket, and individual directions can be 1 0 0, such as this direction will be 1 1 1. Okay. And then if you use a caret bracket, then that will mean a family of direction. So, I repeat that curly bracket is family of plane, caret bracket is family of direction. Okay. So, that means if it is a caret bracket of 1 0 0, then it will be 1 0 0 0 1 0 0 0 1, all of them together. Now, that we know how the directions are indicated, we have to now see that how to find Miller indices of a given plane, because there will be always the crystallographic planes that we would like to define. Now, what you have to do is that you have to first choose origin O okay, in unit cell such that the plane does not touch the origin, that is important. Okay. So, like this is the plane and you can see that the plane is not touching the origin inside the unit cell. However, the plane is closest to the origin. Okay. Now, mark intercepts from chosen origin O along x axis, which is A, along y axis, which is B, along z axis, which is C. Take reciprocal of them, that is 1 over A, 1 over B, 1 over C. Okay. So, what it would mean is that you are essentially fitting it inside a unit cell. So, everything you are basically finding out with respect to normalization with respect to 1. So, if A equals to 1, B equals to 1, C equals to 1, it will automatically become 1 1 1. But if A is 2, B is 3 or C is 4, then it will be accordingly normalized such that it would become half, 1/3, 1/4. So, like that, take reciprocal of the intercepts, that is the condition, and modify the reciprocal if there are multiples there. So, you just divide it by a common multiple. So, reduce the multiples, eliminate the fractions finally. So, finally, you multiply it by a common multiplier and then eliminate the fraction, put bar above the negative integer if there is a negative one. Let us say the plane is in this side, okay, this is positive side. So, anything in this side it is negative. So, then it would become 1 bar, 2 bar, 3 bar, etc. Place round bracket around indices, because I already told you that the round bracket will always indicate that it is that particular plane's Miller index and no commas. So, that is the way we have to do it, and that if you follow for this particular plane, the answer would become 1 1 1, as I told you, that because A is 1, B is 1, C is 1, reciprocal is 1 and there is no reduction of the multiple or the fraction elimination, and it is neither in the negative direction, and hence it is 1 1 1. Now, Miller indices H, J, K are reciprocal of parameters of LMN of each crystal phase. Okay. So, for example, this green crystal phase, you think of it. Okay. So, this will be what? 1 over 1, intercept is 1, okay, and then in one direction it is intercepting, but in this plane is not intercepting with z, not intercepting with y. So, it is infinite distance interception. So, it will be 1 over infinity, 1 over infinity. So, that means it will become what? 1 0 0. So, this plane is 1 0 0. Then the brown phase, this plane, similar logic will become 0 0 1, and the blue phase, this phase will similarly become 0 1 0. So, thus first basic planes for a cube, you can easily find out what will be the Miller index for each one of them. So, that is the first thing we have to do. Keep in mind then now that if I take another parallel green plane, okay, its Miller index will be same, because for all the parallel planes, the Miller index, all the parallel green planes like this, the other one in the other side, the Miller index is same. Okay. So, that we have to keep in our mind. Now, let us go forward and look into the cases that the plane cannot touch the origin and we have to choose the closest origin. So, if you take a problem like this, okay, this is the plane, okay, and then suppose you define everything with respect to this origin, then the plane is not close to the origin. Actually, this origin would have been closer. Okay. So, we can do a origin shift. So, choose a new origin. Now, what is the new origin's definition with respect to the old origin? This is this direction it is 1 and this direction it is 1, right, and z axis 0. So, it is 1 1 0. Now, unit cell intercepts you already are able to find out A, B and C's. So, intercept from origin O prime, you have to find it out, right. Now, this time you see that with respect to O prime, you are going negative in the y direction by half the distance. Okay. So, it is minus half, and then you have minus 1 for the x direction. Okay. So, negative you are going in this way. So, you are -1, and then for the C you are going positive, and that is +1. So, in this case now you have to multiply it by 2, so that you get integers. That means, Miller indexes should be always a full integer. So, -1, -2, 1, and I told you that this minus sign has to travel to the top. So, it will become 1 bar, 2 bar, 1. That is the way, if we have to shift the origin in order to define it with respect to the closest origin, this is the way we are going to tackle the problem and define the Miller index. Now, determine the indices for the given planes where plane cannot touch origin and choose the closest origin. Okay. So, you have the plane, it cuts two of the reference axes x and y. Okay. So, x axis and y axis it is cutting this plane, okay, and at intercepts of a and b. A is half and b is 1. Okay. It is, this plane is not cutting this c axis at all. Okay. So, it is sort of parallel to that axis. So, choose the origin 0 0 0 that you have done. Unit cell intercepts a, b, c, but c is infinity. Okay. A is half, b is 1. Multiply it by 2, it becomes 2 1 0. So, Miller index would become 2 1 0. So, this is a typical case where a plane is neither touching the origin and it is parallel to a particular direction. So, that is the way for such cases, for a given plane you have to find out the Miller indices. Now, let us consider another example. Okay. So, in this case intercepts are half, 1/6 and half. So, reciprocal of the intercept now will become 2 6 and 2, and now you have to divide it, as I told you that divide by a common multiplier, come to 1 3 1. So, then this will become 1 3 1 in this situation. Similarly, in this particular case minus half, half and infinity, again a plane which is parallel to the z axis. So, again this would become minus 2 2 0. Now, you divide it by 2. So, you become minus 1 1 0. The minus travels in the top, you become 1 bar 1 0. So, that is the Miller index corresponding to this particular case. Okay. Now, selecting the origin indices with the bar, for example. So, if there is a bar over the number x, y or z, okay, in that case how we are going to select the origin. So, in that case the new origin O prime should have a 1 in the same place as number with a bar. So, if there is not a bar over the number, the new origin O prime should have 0 in the same place as the non-bar number. So, number with bar, if you get, replace it, n bar equals to 1, and if no bar over the number, n equals to 0. For example, you think of an index which is 0 1 2. Okay. So, there is no change, x 0, y 0, z 0 as the origin, but you get it as 0 1 bar 1 bar. Now, you can shift the origin. You can consider x bar to be 0, no change, y bar instead of minus 1 check it as 1, and z bar also take it as 1. And if it is 1 bar 2 bar 2, then this as 1, this as 1 and this as 0, because there is no change. So, you put it as 0 and then accordingly you do the other two. So, this is when you have to consider that there are negative positions and you need to shift the origin because of it. Now, there are some cases which can be that given an index, draw the plane. Okay. So, the index is given to you. Now, what you have to do is that is just a reverse problem. So, select origin 0 0 0, okay, or if there are negative indices, then origin will be O prime, x prime, y prime, z prime prime. Now, then take the reciprocal of the index values, because that is the way we obtained it at the first place, and then mark intercepts along x, y, z at a, b, c, and draw plane by connecting these intercepts. Okay. So, for example, you see that index given to us is 0 1 1. Okay. Now, you are told that draw the plane. Okay. In this case, there is no negative 1. So, I take the origin as 0 0 0, reciprocal values will be infinity, 1 and 1, right. So, the unit plane intercept for such a case will be such that with the x axis it will be it cannot intercept it, right. So, then you accordingly you can draw the plane so that it does not intercept with the x axis. Now, in this case this plane is something which does not intercept with the x axis and it is on the y and z that it is directly working on, but without ever cutting down the x axis. Now, suppose it is 1 bar 0 0, then of course, I have to change the origin. Instead of 0 0 0, I now do it from 1 0 0, and then the reciprocal values of -1 infinity infinity, and then get the plane and then draw the particular plane. So, that is how given index you should be able to draw the plane. This mental matching you have to do. Now, families of plane, which planes are equivalent? Okay. So, different planes having same index in their Miller indices, not necessarily in same order, is shown by Miller indices of family of planes. Okay. So, earlier we had a simple half moon bracket, and now the entire family is through this curly bracket. Okay. So, if I have a 1 0 0 description, that means of course 1 0 0 0 1 0 0 0 1, all of them, all the variations where only one term is 1 is there. So, it is all these planes are in the same family, these planes and these planes, they are in the same family. Similarly, if you have a 1 1 0, that means any two of the index are 1, that means 1 1 0 is a possibility, 1 0 1 0 1 1, and then not only that 1 1 bar 0, 1 bar 0 1, 0 1 bar 1, negatives also. So, then all these planes that I have shown here, they are part of the family, and then that family we are going to write it with the curly bracket 1 1 0. So, this we have to keep in our mind, because then these are equivalent planes which has the same packing density, it has same environment, and they are will be denoted using the curly bracket. Now, how to find Miller indices of a given direction? So, we have only talked about the plane so far. Let us talk about the direction. So, given a direction, determine the Miller indices of that direction. So, create a new origin O prime at the tail. So, at the tail you create the origin, label O prime and new axis as x prime, y prime and z prime with respect to the tail. Find coordinates from tail at O prime to the head of the direction, okay, and reduce multiples, eliminate fractions using bar for negative, and then you use these closing brackets around the integer. So, for example, in this case I have to figure out that what is the Miller index for this direction. So, what I am going to do, I already know that this part is 1 already, right, is x direction. So, this is 1, okay. So, this is one part, but you are not going towards the y positive direction, but you are going to the reverse direction, and hence this becomes 1 bar, because I shift now to O prime, and with respect to O prime now y direction you are going to the negative direction. So, this becomes 1 prime negative, okay, and then the other part is of course z positive. So, this becomes essentially 1 with respect to the new coordinate system, 1 minus 1 1, right, and that is what we have written as 1 1 bar 1. That is the way we will define the Miller index for a given direction. That means, you have to always transfer the origin at the tail of the direction, and then accordingly that unit cell you have to calculate that what will be the end point indices. Now, drawing direction from indices, suppose we give you the Miller index as 0 1 2, and I am telling you that you find out what is the direction. Now, select origin O at 0 0 0 or choose new O prime if there are negative indices. In this case it is not there. So, I select the origin here, reduce indices to keep direction within unit cell, that means divide it by 2, that's, and then that means it will become 0 half 1. So, 0 half 1 from 0 0 0 I try to locate. Okay. So, x equals to 0. Okay. So, that means it will be in this plane itself, that we already know, and then y is half, that is in this plane here, and then z is 1, yes 1. So, I get this point. So, it becomes 0 half 1 in the unit cell. So, draw direction now from 0 0 0 to this, and you get from the index you can construct that what exactly is the direction. Okay. So, that is the way we are going to quantify the things. Now, just practice if there is a bar there. So, 1 bar, 2 bar, 2. Okay. So, select now new origin, you cannot have it as 0 0 0. Now, it will be 1 1 and 0. Now, reduce 1 bar 2 bar to divide it by 2, minus half minus 1 1, and simply now from this new origin show minus half minus 1 1, and look at the coordinates, draw the direction, you get it. Okay. So, unit cell like that family of planes, again for the direction also there are equivalent directions. Okay. So, the directions in which there will be same property, same packing density, same environment, and this time like single direction is the closing one and all the family will be the caret bracket. So, UVW like 1 1 1. Okay. So, 1 1 1 would mean all these possible directions. So, these are the body diagonal directions. So, this is the family of the directions. Now, suppose I give a problem on the family like identify and draw unit cell families of direction 1 1 0. Then you have to find out all the variations first, and then you have to start to draw each one of them inside the unit cells. The answer would become the face diagonals, which means 1 1 0 means always the face diagonals in each of the face. And if I give you as 1 0 0, then the answer will be all the edges of the cubes that we are going to mention through the direction. Okay. So, 1 0 0 caret is the phases, these directions, and 1 1 0 are all the face diagonals. So, thus we should be able to know that which we are talking about. So, always remember half moon bracket individual plane, curly bracket family of planes, square bracket individual direction, and caret bracket family of directions. You have to keep practice it a little bit. Okay. Now, the important properties of the Miller index, that will be important. Miller index of equally spaced parallel planes are the same. I already told you that for equally spaced parallel planes, the Miller index are going to be the same. Okay. You can try also with two parallel planes and see it indeed remains the same. Miller indices of a plane passing through the origin shown by a Miller indices of a plane parallel to it, because we already said that a plane cannot actually go past to the origin. So, I have to show it by a plane which is parallel to it, and because we already said if it is a equally spaced parallel plane, the Miller index will be same. So, you can always take a parallel plane not passing through the origin. If two planes are having Miller indices H1 K1 L1 and H2 K2 L2, and they will be perpendicular to each other provided H1 H2 plus K1 K2 plus N1 L2 equals to 0. This is something that a corollary of even from coordinate geometry you can get the same conclusion. Okay. So, that is the perpendicularity condition of the two planes. All members of family of planes or directions are not necessarily parallel, right. You have seen it already that these are the same family in the terms of direction, and similarly you can also see when we talked about the planes also that these planes sometimes they are parallel, but this plane and this plane they are not parallel to each other. So, a family does not mean that they will be parallel. Okay? So, we have to keep that point in our mind. Interplanar spacing play a very important role, DHKL, that is distance between planes defined by the same set of Miller indices, and members of family of planes have the same interplanar spacing. So, interplanar spacing DHKL for cubic is cubic side length divided by square root of h square plus k square plus l square, and interplanar angle for cubic cos theta is defined by this relationship. So, interplanar spacing and interplanar angle you should be able to actually calculate once you know the Miller indices of a plane. Now, comes the most important two concepts, which is why I have done all this background for you. One is called the planar density. Planar density is number of effective atoms per unit area divided by the area of the plane. Okay? So, if I give the Miller index of a plane like say 110 plane in the FCC crystal, okay, then you immediately know that 110 plane corresponds to what plane, that you have to identify. You already know from Miller index how to know about the plane. Okay. So, now and you see this is a single plane, this is not the family, there is no curly bracket. So, one specific plane we are showing here, which is 110. On that plane now you start to calculate what are the effective atoms. So, in this case there are these corner atoms 1/4 into 4 corner atoms plus a half into 2, these are the 2 side atoms. So, this becomes 2, and then you can find out the planar density by the number of effective atoms divided by the area of that plane, and that would become root 2 over a square. Similarly, planar density of 111 plane in the FCC crystal, you can again find it out. Now, this is the 111 plane. So, what is the planar density? And you will find it out that this will be 4 by root 3 a square. Okay? Now, if you consider A to be unity, then this case planar density is root 2, that is 1.414, right. And in this case, this will be 4 over something like root 3. Root 3 is about 1.7 approximately, right, approximately 1.7, right. So, you can also now calculate that, okay, then this would become 40. So, 2, 34, 60. So, you have about 3, okay. So, about 2.3. The reason why I am doing this calculation is that you can now see that the planar density of 111 plane is greater than the planar density of 110 plane, okay, for a FCC structure, right. So, this is higher than 110 and any other plane. Therefore, 111 plane is the most densely packed plane in the FCC crystal. Now, this is a very, very important thing. That is why FCC crystals have so many 111 planes, that this system is going to slip very easily, and because of the presence of so many 111 planes, it is ductile in nature. So, thus the planar density, once you know from the crystal structure, that will define the nature of the material, and that will help you to select the particular material. Now, another density is also important, that is called linear density, and that is number of effective atoms on a line and divided by the length of the direction vector. Okay. So, in this case again you can actually calculate that from the Miller index. Now, 110 is the direction, suppose in the FCC crystal, and you find out number of effective atoms on a line and then divided by the length of the direction vector, you will see that 110, that is 110, this line, okay. And earlier we have noted down this plane, right. We have noted down this plane, so that is the 110 plane, okay. But now we are noting down the direction, and this is the plane that we saw is the highest density of the plane. So, that is the plane, and so that means if I try to draw it here, that is the plane which is the highest density, and this is the direction along which the linear density is the highest. Okay. So, For the BCC crystal, this will change. Highest atomic density plane is 110, highest atomic density direction is 111. Now, deformation in metal always depends on the linear and the planar density. Why? Because slip occurs most densely packed crystallographic planes, okay, and along directions having the greatest atomic packing due to low shear stress or energy requirement. Okay. It is like this, that if you have atoms which are far away, then the energy gap that you have to actually cover will become quite large, and hence any slip will be difficult. You need lot of activation energy. On the other hand, if you have very closely packed atoms, then it will be very easy for you to actually slip the plane. Okay? Well, I can give you this example here. Okay? Consider that these are like this, each one of these slips are like this presence of the atoms that we are elongating in one side. Okay? So, look at it in this way, that if I have only two of them, okay, I first keep only two, then in this direction if I have to slip, it is difficult, I need more force. But if you have more rollers with you, you see, then automatically you can sort of deform the whole system, as if you have too many wheels like a caterpillar or a millipede. The more you are having it, the much easier for the plane to move along the direction. Okay? So, that is precisely that happens for a FCC, because FCC has a many of these highly dense planes, and hence it is very ductile. Okay? The dislocations or the slips can move very easily across the planes, but for BCC these are not so many, the density is low. So, it is not so easy to move it. So, BCC is more brittle, BCC will give you less ductile condition. We will see then that what materials offer us this advantage. Now here you have to keep then this point, that the implication of it, that crystal feature FCC is going to have high planar density. For example, aluminum, copper, nickel, the silver and the gold. Okay? All of them have lower lattice corrugation, wider dislocation core, lower unstable stacking fault energy, easier dislocation glide, exactly like I have shown you. High linear density, most continuous, again for the FCC, more continuous atomic chain, reduced local bond distortion, lower line energy, easier dislocation propagation. In terms of another interesting point is, if there is a strong bonding like tungsten, then you get a higher elastic constants and higher resistance to slip. Okay? But this is a case that I will discuss during dislocation. More independent slip systems if you get, then generally you get a higher ductility. That is what happens for all this FCC. Now, if you have a BCC iron, you get high something which is called Pearl stress with respect to this, and there will be greater lattice friction and higher yield strength. So, they are not easily deformable. Now, I am going to do two case studies. Case study 1 is material selection of a single crystal turbine blade. As I told you that for a very long time, these jet aircraft turbine blade was a problem, because you have to design it for a high temperature, because the jet you have to produce, a combustion is taking place. So, the blade has to withstand that high temperature. So, 1000 to 1150, and also a high centrifugal stress 200 to 400 MPa, severe thermal cycling, it is cooling, heating, oxidizing environment and a long service life. So, the blade in such cases must satisfy the high creep resistance. Then of course, there are fatigue, fracture, stability, and it has to be lightweight in nature. So, in such a case then, if you have multiple crystals, polycrystalline system, then the grains are, as you are heating it up, the grains are going to work against each other, and that will create lot of possibilities of failures. So, hence people want to make it with a single crystal, like these are single crystal directions. You can see the single directions in some of the cases easily visible. Now, you see, if I have to choose material, now first of all, how the temperature is going to govern? Well, three candidates: stainless steel, max temperature it can withstand is 700, titanium alloy 600, even lower nickel super alloy 1100. So, naturally temperature wise nickel is the good, and also this super alloy is having a high modulus of elasticity 135 to 300 gigapascal. However, from a product designer point of view, it does not stop there. Even if you say that I am going to go for nickel super alloy, it is a FCC. So, it is a single crystal, right. So, how I am going to orient my grain? Now, there are possibilities of 001. If I orient, it will be 125 to 135. If I orient along 110, that is that diagonal on the plane, then it will be 210 to 230. See, this is increasing. If I am going through 111, the densest one, it will be 280 to 300 GPa. So, my modulus of elasticity will be very high if I go for 280 to 300 GPa. Now, the question is which one we are going to choose? Remember, it is creep. So, for creep, it is important that the thermal stress is to be always relieved, and hence I will not choose 111, but I will choose 001 or 100s, because it is that direction where it is most flexible. So, there will be no thermal stress concentration. So, that is something that is a decision. Okay. Now, I am talking about a case where Miller index is not. So, in this case for turbine blade, Miller index is directly sort of determining, okay, but Miller index is indirect for another case, which is a body in white car design. Okay. Body in white car design, please understand that the car design has gone through a kind of a revolutionary change. Earlier days cars would be having a frame or a chassis, and then on that chassis you have the body of the car. But body in white cars are simply stamped from one single material. Okay. So, it is a concept that is borrowed from aircraft structures. So, you do not have a frame and a body separate, but you take one single material, and then you simply, how do you get it? Through stamping or a forming process you get that entire body. So, this process if I do, now we do not need a single crystal anymore. That single crystal structure is important for a very high temperature case. In this case, what you rather should have are that it should be lightweight, it should be crash worthy, and formability should be there. So, in such a case, we can go for a polycrystalline system first of all. Secondly, I do not have a high temperature requirement, but what I need is a good workability. So, steel or aluminum is good for us. Next, what are the Ashby indices? That we already know that against stiffness, Ashby index is e to the power 1/3 over rho. Against strength, it is sigma I y to the power 2/3 over rho, and against these energy absorptions, it is sigma y epsilon f by rho. Okay. Each one of them is specific. Remember, I told you that in this particular session, we are always thinking of lightweight structures. Lightweight is absolutely important for a car design, because as the weight is less, then the fuel consumption will be less, okay, and you will get a much more better efficiency of the system. Now, how the Miller index will indirectly affect here? Well, of course, if you go for a polycrystalline system, you are not maintaining a single crystal direction like that we do for here directional solidification. We do not do it, but you can still actually do the rolling and stamping by creating a preferred grain structure. That is what people follow, that what is the grain structure, because along the grain structure you can have more strength. Okay. So, corresponding to the same weight, you get more strength or more stiffness that is more desirable. So, you can control the grain structure for such a case, and again the knowledge of Miller index will be important for you in order to define the grain structure, the sort of what you call the direction, the grain texture direction. Okay, so I think this is where we close now. In the next lecture, we talk about crystal defects and its effects. Thank you.